TotalView is actually a part of RogueWave. It's a larger organization which has acquired other companies. So the debugger is not just what we do. What we do is, RogueWave's motto is to help organizations simplify complex software development, improve code quality, and shorten cycle times. We have a lot of different products. One of the most recent ones that's kind of interesting that apply to this crowd is Clockwork, which does static code analysis, which is analyzing your code actually before you run it and debug it. It doesn't work on multiprocessing and multi-threads, but it does a good job of organizing, analyzing it, finding problems before you do that. We have OpenLogic, which is used to analyze open source code. There's open source auditing, management, support. So you can find out whether or not you're using something inappropriately or don't have the right licensing for it. IMSL is math libraries. SourcePro, I think it's somewhat like that too. As PVWave we also use PVWave for visualization, so all those. I must admit that I just know TotalView. So, but some of the other things do sound very good. We have a global diversified customer base, so if a lot of you people are graduate students and are going to be going out into the industry later, you can see that we have a wide group of industries, financial, telecom, government defense, technology, other verticals. We're in most of the animation studios, which I've got to visit a couple of times, so that's kind of cool. Debugging occurs in many of these industries, of course, financial services. I mean, those companies that we just saw before were using all our products, not just TotalView, but the ones that we use, financial services, oil, gas, aerospace, they're all the same type of thing. Of course, then we get down to the ones that we're interested in here, scientific and technical, and high-performance computing. So what we see with HPC, which we need to debug, we see a lot of things going on. We see clusters getting NVIDIA GPUs. They're starting to use the Intel Xeon Phi things. We have complex memory hierarchies, NUMA, non-uniform memory access. We have device versus host. Custom languages such as CUDA and OpenCL. Directive-based programming such as OpenACC and OpenMP. And the core and the thread counts keep on going up. You saw that slides of the systems that are using more than 10,000 cores and stuff. So it's a lot of complexity if you want to deal with it, if you want performance. C or Fortran with MPI starts to look simple when you start adding in all these things with the GPUs and the Xeon Phis. Everything is using multiple language and parallel paradigms. We have C, C++, Fortran. You have up to 4 different kinds of parallel. You could have it parallel on the cluster. You have OpenMP, which is your thread. You have mix of OpenMP and MPI, and you have your vector processing. And then you have to deal with data movement and load balancing between all the systems and such. So how does RogueWave help? For this purpose, and for the thing that I know best, is the TotalView debugger. So it's a debugger, basically. You use it to analyze your code. We work on C, C++, and Fortran, OpenMP, MPI. We support for most HPC platforms and languages. And if some of you are students still here, we have a Student Express license, which is available for both undergraduate and grad students. It's free, which you can use on your personal workstation or laptop up until the time you actually graduate from school. So I think that's a nice little program there. TotalView has been around for quite a long time. It was this is a picture of the butterfly machine, or a diagram of what it is, from the mid-1980s. It was built by Bolt, Beranek, and Newman, the BBN. It was an early, massively parallel computer. You can see that this diagram has 32 cores on it. So you can find that in some workstations these days. It was called the butterfly because of the design of the interconnect. Maybe you could make a butterfly out of that. I'm not quite sure, but TotalView. So how do you debug on a butterfly? The TotalView project was started at BBN back in the mid-'80s, just for to solve the problem of being able to debug programs on something that has multi-threads and multi-processes. How do you attach to them? Instead of just attaching one to one, you want to attach to all of them at the same time. So it was designed as a graphical interface at first, based on Motif and X11, point and click. We show, of course, C, C++, and Fortran. Of course, we show assembler too, which is sometimes all you see when you run across code that's been optimized or you forgot to add the -G when you're compiling. But unfortunately, the butterfly machine never really took off. They were designed, I think, to be a maximum of about 512 processors. Typically, they are sold in 16 or 32 processors. But the TotalView group lived on. We ported TotalView to many other machines, IBM, Cray, Solaris Spark, DEC Alpha, which is one of the debuggers that I had worked on in the past, IRIX, HPUX, et cetera, et cetera. Then as various MPIs were developed, Bill Grupp and Rusty Lusk, Jim County was a TotalView employee. We were called Etnis at the time. They worked on a interface which would allow you to do automatic process acquisition. I've seen quotes by Bill that this was not intended to be a standard, but other people reversed engineered it, and it's become widespread through most of the MPIs you'll see. So it's an MPitch, it's an OpenMPI, there's an LAM MPI. So it's easy to do. What that involves is that there's a structure which, when the process goes parallel, the structure gets filled in with the nodes that are being used, the processes that are being attached to. So that gives us an easy way to figure out what we needed to attach to and which processes. Some years later, Bill and Jim worked on another interface which allowed you to track message queue information. We're not tracking all the messages that are passing back and forth. We're just tracking the ones that haven't been consumed yet. So if something gets stuck, then you can take a look to see where the messages are. And as time went on, we added other capabilities. Support for most types of MPI, Linux. There's an odd story behind that. I guess back in the mid-'90s or early '90s, the CEO and president of Etnis at the time wasn't really convinced that Linux had any life in it. So he didn't want to really spend the money to port to Linux. Jim County, who was mentioned in the other slide, decided to do the port by himself. Now Linux is probably 80–90% of what we do. We added lightweight memory debugging. We have type transformations, memscript and tvscript, which are ways of running in batch mode unattended. Reverse debugging, which is really kind of neat thing. Fortunately, reverse debugging only works on the Linux x86 and x86-64 platform. It's not available on Blue Gene. Remote display client, which is similar to what David was saying about the native client. It's not quite as sophisticated as what they're using, but it works pretty well. And of course, we have GPU debugging and debugging on the Intel Xeon Phi. So the key features of TotalView are interactive debugging, interactive memory debugging, reverse debugging, and unattended debugging. Works on serial, parallel, and accelerated applications. So what is TotalView? This is our first screen where we get to see a shot of what it looks like. We will admit that the interface has been described as somewhat dated. A number of years ago, we moved up into the 1990s. And so it's not quite as sophisticated as some these days, but it's not too hard to use. Up in the corner, we have the stack trace. Over here is a stack frame. The source code, of course. Down here is something that you will not see quite as much these days. This is an earlier screenshot of TotalView. The processes tab is something we found that wasn't very scalable, because if you start filling in thousands of boxes just with the state of the debugger or the state of the process, it just got hard to maintain. But we have, but this is it. It works on laptops to supercomputers. Supports most Linuxes, Unixes, and also runs on your Mac laptops. I see a lot of you people have Macs here, so you can run debug directly on the Mac, as well as use the client to hook up into the supercomputer. And it does the normal type of things you learn. Parallel debugging, we use MPI, pthreads, OpenMP, Fortran coarrays, CUDA, OpenAC, and on the Intel Xeon Phi. There's a low tool overhead, resources. We try and make when we're going across a multi-process environment on multiple nodes, we have debug servers which are controlling those processes that are running there, and they're very lightweight. The remote display client, memory debugging with memory escape, the replay capability, which is the reverse debugger, and batch debugging with TV script and CLI. We also have type transformation and C++ view to transform user-defined objects. So things like STL structures, maps, lists, strings. Many of those are automatically built in, and you can also define transformations for yourself, for your own structures. What is memory escape? Memory escape is a slightly newer interface. We use it to detect runtime memory analysis and eliminate memory errors. You can detect memory leaks. You can explore memory heap usage. This is a view right now, the heap status graphical view. You see things over here, all in red. These are leak blocks. These are ones that are in use. The darker ones are unallocated blocks. We have a tooltip type functionality where you can just hover over one of those blocks and it'll give you this thing that tells you which allocation block it is, where it was allocated, and how many are allocated such. And again, it supports all the major platforms we have. We'll detect things like buffer overflows. We have a couple of different ways of doing that. There's guard blocks. We basically are allocating extra blocks at the beginning and the end of yours. We allocate a little bit more memory than you usually requested, and we'll put blocks at each end of that allocation with a pattern written into it. So if somebody writes over that, that'll be detective. That will not stop your process in real time. We also have red zones, which will stop your process in real time because you're allocating up your block. We try to line it up against the edge of a page, protect the next page, and whenever you run over that, the process will immediately stop. But most of the time, it's low runtime overhead. What we do is you do not need to do any special compilation to get memory debugging. The only thing that I suggest is if you're doing it with an MPI program that you link against the agent. But basically the way it works is that the interposition library will sit in between your program and the system libraries, and it tracks things as they're going back and forth. So we can know exactly where your block has been allocated and how large it is. We can do manipulation with guard blocks and stuff. You can hoard memory so that it's not immediately freed back into the system, and that can show you where things are going wrong. It's a very useful tool. Replay debugging is really very kind of neat. It only works again on the x86 and x86-64, but it allows you to record your program as you're debugging it, records all the state of the program as it changes, so that as you're going, you can actually let the program crash, if that's what it does, and then you can go back and go backwards in time and see exactly where that program crashed. So you can take it. I've seen cases we have where it'll totally destroy the stack, and so that you can't see anything. You walk back, you keep on going back until you get to a point where the stack comes back again, and you realize that's where things have been trashed. I use it all the time myself. What this is showing here is this little blue arrow is the live point. The yellow arrow is actually where you've gone back to. So you can keep on going back in time to see how the values change. And walk back and forth. And you'll go back and forth. I was tracking problems myself, and I'll go back and forth to see where it crashed, and I'll go back and go to this thread or go to that one. And it eliminates the restart cycle, so you don't have to recompile. You can just run it once, see it crash, come back, and walk through things again. You can step back and forth by function, line, or instructions. You can, as these icons up here, the next is typically when you're debugging a program, you're nexting over any calls. Step is you're stepping into a call. So these would be previous. We'd be going back over a call, and unstep might step into a routine that you've just come out of. You can go back to the caller, and you can also go back to the live point. And we've just added something about saving this too. This can be, there's replay on demand, which you can run your program to a point where you say, well, there is a bit of overhead in reverse debugging that can't be eliminated. But you could run to a program to a point where you say, okay, I know it's good here, and I want to go to a place, I want to turn on remote debugging here, because maybe your program's been running for like 15 hours before it crashes. So you run it 14 hours, then you turn on the replay debugging and continue from that point. And this is supported on, well, on Ethernet, InfiniBand, the Cray systems. Supports pthreads and OpenMP, so you can go back and forth between threads. It does support MPI. You can start up your program in MPI under replay debugging, and that'll record all your processes. Or you can choose replay on demand and just look at those processes as you want to and set those to do replay. And the new feature up here, which I hadn't even noticed before, the save function, that's our new save and load replay information. So you can record this, save it, yep.
How do you actually implement this going backwards?
Well, it's actually a little bit like a DVR. So we are collecting data as we go along. We take snapshots of the state of the program. As anything changes in it, that we save that. We're going instrument by instrument, instruction by instruction. So this is all, it's recorded in a file. And there is a memory issue where you could run out of memory, but we have a circular memory buffer. So as time goes on, some DVRs, they'll save like the last half hour of your program. So you can go back a little bit. We're just doing the same type of thing here.
Because you could go out of scope, and then when you go backwards into the scope, you don't know what is the value to start with, because unless you have saved it, yeah.
Yeah.
Save the state every.
You save the state. It's almost at every instruction step. But it's a really neat fixture. You go back and you can see how the values change. You may go from where a value has not been initialized yet. You can see it as some large thing until where it is initialized. And you can't change the data that's already been recorded. It's saved data, it's recorded, but you can go back and forth through that to see where things are, and you can go off on different threads if you need to. So it's all deterministic, though. It's all, everything that's happened before will happen again. So, but if you capture that crash, it's kind of a nice thing to be able to find it that way. MemScript and TVScript, these are command line invocations to run TotalView and MemoryEscape unattended. TVScript is running TotalView itself. MemoryEscape is actually a subset of TotalView. They decided at some point that it was people who just wanted to do memory debugging. So we have MemoryScape by itself, but underneath it's all really TotalView. It's all bundled together, but you can look at it separately. TV script can be used to set breakpoints, takes actions at these breakpoints, and have the results logged to a file. It can also do memory debugging because it's all part of the thing. So a typical thing here might be, this is an invocation line. TV script, you use a create action point. You can set it, there's a couple of different ways of setting the breakpoint. You can do method 1, which is just a routine name. Display backtrace, show arguments. You create a action point on method C, which is your program itself at line 342. And at that point, you want to do print X on my program. My program is actually the program. A dataset 1 would be any arguments that are done to the program. Memory script, as can be expected, is a subset of things. It can run memory debugging, but you can't do things like set breakpoints or so. So it's just capturing memory events as you're going along. Exit is always considered to be a event. So we're always going to stop at the exit point and collect data at that point. So you can give it an event action. Here's just an example I picked up is alloc null. So if there's a null allocation, which is one of the types of memories errors you can run into, you can list allocations. At any event, we might want to check guard blocks to catch overruns. You turn on guard blocks, of course, give it a max runtime, and you can show what you want to display. Don't show the PC, don't show the block address, show the image though, and again, my programs. The MemoryScape data can be saved in HTML files into a memory debug file, which can then be loaded back into your program and inspected there, or just a text file showing the heap status. This is one of the customers that I talk with. So they used it to identify memory issues, and by using the scripting interface, by using MemScript, what they've done is they've built it into the production cycle so that every night they compile their code every night, run it through MemScript, and they use that to find out what has changed in the memory. So you can find new memory leaks and such that are been added. They were struggling with intermittent errors, which are caused by memory, but now since they had it built into their product, built into their production cycle, they get better code, quality code. The remote display client I want to talk about. Now, if you're pushing X11 bits and events across wide networks, that can be painful. I'm sure people have run into that here. What we have on the Windows or your Linux client, you're running it on your Windows, Linux. There's also a Mac client. So you start it up here, and then you launch it to run over the network. It'll start up a debug server on the remote computer, which will start up a VNC server there, and then talk back and forth. The VNC configuration is quick, so it's almost as if you're sitting directly at the computer. I have a setup here. I've been testing this out at Argonne. So this is the type of thing you'd enter. The first line, you give it the remote host, a Vesta, username. If you need to go through some sort of gateway system, you would enter that in the section 2, give it all the systems that you would have to go through to get to the target system. And then you give it the path to TotalView on the remote host, soft debuggers. If you already had that in your environment, you can just put in TotalView there. This one tends to confuse people a little bit just because of where they expect your executable and the arguments and such to be. Since we're really starting TotalView on the MPI starter, here at Argonne, it's a run job. The arguments that we're passing in are the typical things, NP512, block, COBOL part name. That's actually a bug that I found that we're not actually passing in environment variables at this point. It's not that typical problem, but if you, it took me a while to figure out why my why my remote batch job wasn't starting up. And it was because that once I figured that out, I was able to correct that. We set it to be custom, where you do PBS and LL, load leveler. But once you can set it up to be any type, really. Just tell it custom, and you give it the submit command, which here is qsub. This will execute a little script on your system as well. It'll take all the information that's in the first part, construct an SSH script, and then pass that off to the batch queuing system. And I was playing around with that last night. It works pretty well. Support for new platforms. I think this is not quite new platforms, but because some of them have been around for a while. We have TotalView for the NVIDIA GPU. We support all the latest versions, 6.0, 6.5, and 7. We support dynamic parallelism, clusters, and multi-card configurations. And there's a flexible display and navigation on the CUDA device. Up here, we'll see this is the physical display. It'll show the device, the SM, the warp, and the lane. We can also look at it in a logical format just by clicking the physical here. That'll toggle between physical and logical. And in logical, it'll display the grid and the blocks and such. We have a CUDA device window, which I'm not showing here, but it'll tell you what things are actually available. I like bringing that up when I'm giving demonstrations, just to show you what actual lanes are available to use and such. So we have these little spin boxes up here, which you can change to look at the device, the warp, the lane, or the grid or the logical blocks, and that'll, looking at the device window, basically tells me which ones are valid to use. We support core debugging, and we also use CUDA memcheck, and we have support for OpenACC.
Regarding the CUDA debugging, what kind of state does the core file capture? What if there are multiple kernels running in parallel?
Good question. I think it'll display the state of the CUDA warp, the whole state of the CUDA device, CUDA kernel at the point that it crashed. So it should come up. When you do that, it'll come back up and it'll show you where everything was at the time that it crashed. And you could probably go through all the different threads at that point.
But will it restore the state of the blocks and warps running?
Yes. I mean, it's not going to get you back to a point where it was running, but it'll show you what was running, what the state was at the time of the crash. So for the Xeon Phi, it's a very similar type of thing. You can use it in native mode with or without MPI. You can use offload directives, which send it off to the mic. You can mix it with OpenMP and the offload directive at the same time. Symmetric mode, host and coprocessor, multi-device core clusters, that's all available. It uses all the MPI debugging features, process control, view across, shared breakpoints, and heterogeneous. You can debug both on the host and the mic at the same time. And we have memory debugging on both native and symmetric modes, so you can see where allocations and such have taken place. And we anticipate support for Knight's Landing in late 2.15 or early 2.16. I'm not quite sure how close late 2.15 is going to be, since we're still waiting access to a Knight's Landing machine. We know that we'll be able to take use of memory debugging. The Knight's Landing will have the high bandwidth memory on the board, and it's set up. Memory Escape will be able to use to track those allocations both on the standard heap and on the on-chip HBM. We also have support for Linux OpenPower, which is the little ND Power PC machines. Those will be used in the Coral at Lawrence Livermore, and I think Oak Ridge might be getting the same type. No? Oak Ridge, yeah. We actually have a version of that ready right now. It's still early access. One of the problems seems to be that the Linux Power LE that we have keeps on crashing on us, and so we tends to hang and crash and has to be rebooted every time. So, but Nikolai Piskin, who is the choice number 2, if you contact him, he'll be glad to give you access to that. Current work and future plans, TotalView 8.15, scalable infrastructure, faster startup on Linux. We have been using MRNet, which is a tree-type structure, much as David's describing in some of his. So it basically, we have debug servers sitting out there on the machines. It's scalable. We want to push the smarts to the back end, but not the whole debugger. So we use a classic technique. It sets up a tree structure on the top, fans it out to the control nodes, COM nodes, and then each of those will control different TV servers. So trying to remain lightweight in the back end. Servers don't steal memory from the application. Each server is a multiprocessor debugger agent. So one server can debug thousands of processes. It's not a collaboration of single process servers. There's not a one-to-one server, debug server to the process. So there's no artificial limits to accommodate debugger. There's not one processor per compute node. Symbols are read, stored, and shared in the front-end client. And for an example, we have just to give an idea of the sizes that are being used. The TV client itself, which is running on the head node, is using about 4,000 megabytes. The COM node is a little under 500 megabytes, and the server itself is only using 304. And on this, we had a 64p job. There was 4 COM nodes, 16 processors per COM node, and 1 server per COM node. And the startup performance is, we have recently released 8.15. We're up to version 7 right now. But between 8.14 and 8.15, we're seeing 5 times faster at 16K between 8.15 and 14, and that's basically we switched to using MRNet as the default. This is on a Linux system, and the lines here, this is the startup time for not using MRNet. You see 600 seconds up there, so that's a good 10 minutes. And down here, we're down to about 150 or so. So still a little bit of time to acquire all of them, but we're getting better at it. And the Blue Gene startup time is also very nice. It's better than some of the Linux systems. 100 seconds over here, we're down to about 25 to 30 seconds here for 18,000, 16,000 nodes. This is the picture we used at Supercomputing a while. We debugging on 786,000 cores. And we realize our interface is a little bit old, so we're coming up with a new revolutionary. I wouldn't say it looks kind of like Eclipse to me, but you can see where we're trying to come up, and you can use it to design your own debugger tool. You can move these windows around and do various things with them. And that will be in our evergreen beta soon.